Greetings and welcome to a C++ lecture. Okay, we're talking about references today because we need to start talking about those. Very important, well, the concept of programming in general, but especially as to why you would deal with the aggravation of C++, and that is its ability to directly manipulate memory compared to most modern languages. All right, so review. Memory can be thought of in terms of mailboxes. So if I've got a chunk of memory, each particular byte of memory or section of memory can sort of be seen as its own little box. And when I declare variables, those variables are basically assigned to one of these mailboxes. Remember, each one of these boxes has its own specific numerical value. Underneath the hood, underneath the hood, at some point, when you refer to the variable x, you are referring to memory location 125. Which again, remember, this is why we need to understand these things, because this has a whole series of knock-on effects, right? If I need to represent each one of these memory locations, whether it be RAM or physical hard drive locations, with a numeric value, then I am limited to the number of locations by how large of a number can I represent. So when we had 32-bit stuff, that meant we only had 4 gigs. The max unsigned range of a 32 is 4 billion and change, right? Or 4 gigs worth of memory. Which is why in 64-bit operating systems, we can have hard drives larger than 4 gigabytes. Again, remember, there was a dark age in which we were limited to 4 gigabyte partition sizes for our hard drives. In any case, getting back to the memory, when I create variables and I say, x equals 5, y equals 6, and z equals 7 in my code, it's going to go and find those locations in memory and store those values in there. But now we get to get a little bit more specific about what type of memory are we talking about. This is what's called a stack, and let's assume that we are inside our main function. Whenever we have a function in C++, it is going to be assigned what is called stack memory. This is also, consequently, why one of the most popular question and answer websites out there is called Stack Overflow, because that is I wouldn't say easy error to get in C++, but it's a somewhat common one to try to assign more information, more memory than what your stack has allocated to it, and you get a stack overflow error. But again, we've got our main function. The main function has its own stack of memory that I can assign values to. Now, let's say that we have a function called stuff. Well, stuff is also going to get its own stack to store variables in. It's worth noting, not that we're going to deal with it in this lecture, it is worth noting there is this thing out here to the side. We'll call this the heap. And this is everything else. This is basically the rest of your open system memory. We will come back to the heap because that's very important once we start dealing with pointers. We're not quite there yet. So coming back over here to our function called stuff, anything that goes on inside of stuff is going to be on stuff's stack, even if it's the same variable name. So let's say inside of stuff, we have variables x, y, z as well. We say x is equal to 10, y is equal to 0, and z is equal to -1. Because why not? Well, in stuff stack, you're going to have x, y, z, and the values 10, 0, -1. An important thing to keep in mind, a critically important thing to keep in mind, actually, is that a stack only exists while its function is active. So the main stack will always be active, because once the main function ends, your program ends. So main's the only stack that always exists during the lifetime of a function. But when I call the function stuff, this stack gets created, and then when the function ends, that stack gets deleted. Don't want to actually erase it. So let's say over here we've got the actual code for my main function. So I'm going to assign my values. So I'm going to say x equals 5, y equals 6. Oops. Y equals 6, not p. And z equals 7. Let me get that z a little bit better there. Even with a drawing tablet, this is a little interesting. Okay, so I've got that there. And then let's say I want to print out the values. I'm just going to write PV to keep things short. Well, the output is going to be 5, 6, 7, because that's what the values are there. At the moment, oops, didn't mean to get that excited with the erasing. At the moment, stuff doesn't exist. This function hasn't been called. Its stack does not exist yet. So let's say I call the function stuff, and the function stuff basically takes 3 variables. Again, the variable names don't matter. I'm just using x, y, and z. I'm using the same variable names here to illustrate the fact that just because they've got the same variable names, they're not the same variables. And inside of stuff, I don't know, I'll say x equals y plus z, and z equals 2 times y. And we'll just set y equal to 0 after that. I don't know. Just random operations, mainly. So that's what stuff does. So back over here in the main, we have x equals 5, y equals 6, z equals 7. So those values get stored in the memory locations in that stack. Print them out. So we print out 5, 6, 7. And then we're going to call stuff. So now we're going to come over here to the stuff function. Now the stuff stack exists. I'm going to say x equals y plus z. So I've declared x, and I'm going to store the value of 13. Again, we are in the stuff function, so we're working out of this stack here. I'm going to say z equals 2 times y, so 12. And then I'm going to create y and assign it the value of 0. And then the function ends. Which basically means once this function's gone, all that location in memory is released. It no longer exists. And keep in mind those values are still technically there. It's just nothing's pointing to those values right now. This is why it's always so important in C++ to always initialize variables before you use them, because you have no idea what kind of junk data might be left over in here from other programs. So we've come back to main, And let's say we print out our values again. Well, what are the values? 5, 6, 7. Nothing's changed, right? And ideally, you should have an idea of this. Like, this shouldn't be shocking news to you at this point, because that's how functions work, right? Unless you tell them otherwise. If I have this stuff function over here, and I pass in variables and manipulate those values and stuff, it doesn't matter what I do inside this function, those values will not change back over here in my main. But what if I want that to be the case? What if I want the information I do over here and stuff to be reflected back over into main? That's where we get the concept of pass by reference. All right, so let's go ahead and get a new whiteboard set up. Take a look at this. So I'm still going to have, of course, my main stack. And I'm still going to have stuff when it eventually gets called. And stuff will take XYZ. Notice I'm putting an ampersand in front of thing. Oh, I royally butchered that one. But notice I'm putting an ampersand symbol in front of these. That's the symbol, by the way, in C++ for indicating that you are doing something by reference. You're getting fancy with your memory, is what the ampersand symbol indicates. So over here in main, again, we'll say x equals 5, y equals 6, z equals 7. So when I execute that code, I get x, y, z, and 5, 6, 7. Now I'm going to call stuff x, y, z. But now stuff has been set up to pass by reference. Go ahead and write that down. Pass by, I always spell the word reference wrong, although I do know that it starts with an R and not an F. It's like I'm pretty sure I'm missing a letter in there someplace. Pass by reference. So stuff has been set up to do a pass by reference. What does this mean? Well, of course, we've got, through the function parameters here, the variables x, y, and z have been defined. But when I call the function, normally when you do a pass by value, which is the example that we just saw, I would copy the value 5 over here, copy the value 6, copy the value 7, and there we go. That would be a pass by value. I'm copying the values. However, when we do a pass by reference, what I am instead doing is I'm sending over the memory location. So what x actually has is a reference to whatever was passed in. Same thing for y. Same thing for z. Again, this is a very important, critically important thing to understand with pass by reference. When you do this, when you pass by reference, you are not copying over the values. What you're copying over is the memory location for whatever's being passed in. This is critically important to understand. So now, over here in stuff, when we have our operations where we say x equals y plus z, z equals 2 times y, and y equals 0. When I say x equals y plus z, oh, this is referencing over here, 13. Z equals 2 times y. There's z, it's referencing over here. Y equals 0. Y is referencing this memory location. Function ends. You get the idea. The function ends. This data no longer exists. None of this data here exists. And now over here in main, if I go out to print my values, 13, 0, 12. Because, again, when we called stuff, we did not copy the values of the variables over. We copied their memory information over to use. Now you might be wondering, okay, well, that's a nice, fine and fancy little trick. What would you use it for? Well, I just demonstrated one thing that we would in fact use it for, and it's very commonly used for. What if I need to modify the values of multiple variables? So remember, a standard function now, a standard function can only return one value, right? But if I need that function to return two things, maybe I want it to return two handles to two different files. Or maybe I'm loading information from a file and that information needs to be stored in several different variables. Or I just, for whatever reason, I've got these three values here and I need to scale them. So like I'm trying to like rebase the numbers or rescale the numbers to be on a different scale, and I need to modify all the values that I pass in. There's a considerable number of scenarios in which you would want to modify values like this. There's another thing that gets passed by reference sort of automatically, and that is arrays. So let's take a look at arrays real quick. So let's say that we have sort of a basic int x. Let's say it's a three-dimensional array, and we've got the values 1, 2, 3 initialized, right? Yeah, so, standard array stuff. If I reference or try to print out x of 1, that's going to print out 2. So how does this look on the stack? Oh, if I have the main stack over here, it's a little bit different, right? Because I can't just say x equals 5. That doesn't work. Instead, what happens here is when I say x bracket 3 like this, what happens is x is assigned to a chunk of memory. And so if I come along and then say just a regular old int y equals 7, y would be assigned down there. And if I want to reference any of these specific cells, that's why we have to use the square brackets syntax here. So that way I know what offset am I looking at? Am I looking at offset 0? Am I looking at offset 1? Or am I looking at offset 2? Hopefully this syntax now is beginning to make a little bit more sense looking at it in terms of memory. So when I reference x of 1, I'm saying, okay, I'm going to go to x's memory space. My offset is 1, so I'm going to read this value out of it. So that's what's going on at a baseline level for arrays. But what happens when I have an array in a function like this? I want to pass in an array to this function to do stuff to it. Maybe what I want to do is I want to go through and add 1 to every value inside this array. Well, something interesting happens here. This is a surprisingly complicated problem compared to the solutions that we have available in other languages, like, say, Python, Java, or C#. Again, getting back to that point of many modern languages were written almost in response to some of the weird idiosyncrasies that C and C++ have. So let's look at this. What's going on here? So I have my stuff stack. That's going to be created when I call that function. Now here's the interesting thing. It doesn't matter whether I say int y empty bracket, bracket 3, bracket 30, bracket 4592. It doesn't matter. It all might as well be empty bracket. Because what's happening here is it is passing by reference the start of the array's memory block. This is what is happening here. So when I say void stuff int y square brackets, when I call this function and when I pass in this value, so when I say, now they realize that is a horrible spot to write that. Let me rewrite this here real quick. So over here in main, when I say stuff x, because that's how I would call it. Again, I do not want to say, this is wrong. I apparently want to really write T's. I really want to write F's today for some reason. I better not grade things because apparently I'm really fond of the letter F right now. I do not want to call stuff, say, x of 0. That is not what this function is looking for. That would be if I had a function that was like, I don't know, void junk, just because this is a junk example. If I had a function definition like this, that's what I would do for that. Because x of 0 is very specifically passing the value of this right here. So when I say x of and I give it an offset, basically that can be treated as just a plain old regular old integer. So that is not what we're looking for. If I want to pass the entire array, not a single element of the array, I want the whole array, I do not include the square brackets when I pass it in a function. I just say stuff parentheses x, and that is going to pass the whole array. Kinda. It's going to pass it by reference. So again, what happens on the memory level when x gets passed in here, we create the variable y, but we do not copy all of the values over. Instead, all we do is put in a reference to the first location for this array. And then if I reference, say, y of 2, y references over here. What is my offset? 2. Offset 1, 2. I will pull out the 3, as expected. But this creates a little bit of a problem. How do I figure out how large this array is? Because again, it doesn't matter if I put a 10 in here. It doesn't matter if I put a 1 in here. What is going to happen when I pass this array into this function is it's going to pass by reference the memory location of where that array starts. Very important detail to keep in mind. But it's also a little bit easier to understand what's going on when you see it in action. So let's go ahead and switch over to code. All right, so what do we got going on here? We got a couple of functions to show off the whole difference between pass by value, pass by reference, and the insanity that happens with arrays. Let me take that out from, had that in there for my testing. So let's take a look at this add one to all function first. I'm passing in 3 values. Now, when I want to indicate that I am passing by reference in C++, like I mentioned in the whiteboard section of this lecture, you put the ampersand symbol, Shift 7, had to look at the keyboard there for a moment. My fingers know where it is, like, what number is that on again? But yeah, Shift 7 gives you the ampersand symbol. And that informs the compiler that, hey, I don't want to copy the value of whatever's being passed in through here. I want to copy a reference. I want to copy the memory location of what's being passed in. So A is by reference. B and C are not by reference. They are by value. In other words, the way we've typically been using variables and functions. So let's take a look at the code here. So I've just got some basic initialization. X is 0, Y is 2, Z is 4. And then I'm going to call add one to all, pass in XYZ, and then print out what the values are. And we'll come back to the array stuff here in a moment. So if I run this code and get my output window over here, the values are 1, 2, 4. And if we come back up here and look, I'm adding 1 to all of these values. But since A was the only one that was passed by reference, that's the one that actually gets its value changed. Again, let's step through this here. So I'm going to put in a breakpoint, run my code, and I can see the values of x, y, z are 0, 2, 4, as expected in this point in the code. I'm going to step into my function here. And as expected, now that the function has properly initialized, my values for A, B, and C are 0, 2, 4, because those are the values that were put in. And so then I go through and execute the code. Bam, bam, bam. There we go. And A, B, C, as expected, the values are now 1, 3, 5. Now when I return back to main, now this function has completed. Let's just go ahead and move the line of execution down to get ready to do our cout statement here. We can see that, yes, okay, x has now been changed. Y and z are still 2 and 4, because again, they were passed by value, not by reference. But since x was passed in the by reference slot, its value has changed. So that is a basic demonstration of passing in something by reference versus value. This works for any and all data types, whether it be structures, classes, strings, characters, ints, floats, bools, you name it. If it's a variable, you can pass it in by reference or by value. Although when it comes to classes, there's some extra considerations to keep in mind for that, which we'll get to once we talk about classes. All right, so let's deal with this array nonsense. So running the code, we can see I've got 2 array links here being printed out. So in main, I am grabbing size of test. Remember from, assuming the sequence hasn't changed, last week, if I do size of and then a variable that is an array, it is going to tell me what is the total amount of memory that has been assigned to this array. Again, going back to our whiteboard example here real quick. Remember when I declare an array, int x bracket 3, it's going to assign a chunk of memory to that array, and it knows, the array knows what its assigned chunk of memory is. Right? So that is how when I say size of test, test being an array, it knows to be able to say, oh, I'm 40. My size is 40. Because again, a integer is 4 bytes. But now something very interesting happens when we do size of x in the function. It says that the array length is 8. That's not right. Okay, so again, what's going on here? Let's put a breakpoint in right here. Run our code. And so what is going on here? And sure enough, length is 8. It's reporting that the size of x is 8. And it's worth noting, by the way, actually, let me take that breakpoint out. It doesn't matter if I put a 5 in here, which is clearly not the same size as test, right? If I put a 5 in the function definition, still 8. I put in a 50, still 8. I match it perfectly so that it's 10. You guessed it. Still 8. It does not matter what I put in here. Like I said back in the whiteboard section, when I pass in an array, it is not going to copy all the values of the array. Which makes sense. Like, this is actually how you want the program to function. Because just for demonstration purposes, our arrays have always been fairly sane in their size. Imagine that you have an array of height map points for a video game. You know how the terrain, like to define the terrain, like how high every single point on the terrain is. That's usually done with a technique called a height map, where you've got a grid of data points that you say this is the height offset for these various points. And it's very common for that height map to be a, like, say, 512 by 512 texture, or a 512 by 512 map of data points. And that means if I need to store all of those data points in an array, I need an array that has 262,144 elements. I do not want that copied every time I send that array into a function. That would be horrifyingly bad for performance. So, yes, this behavior is what we want. Doesn't make it any less annoying to actually deal with it, but it is what we want. And now, why is size of reporting 8? We'll get to that once we start talking about pointers, which will be next week. But it's because, technically speaking, under the hood, this is a pointer, and that's why size of is reporting 8 instead of 4. Regardless of that particular explanation, we still run into the issue of, well, if I want to add 1 to every element in this array, how do I find the size of the array? You don't. Yeah, it's a little bit of a trick question. It's a bit of a gotcha, especially when you have learned other languages prior to coming into C++. Because, again, to list off my favorites, Python, C#, Java, JavaScript for that matter, if I'm remembering correctly, PHP, it doesn't matter. If it was a language created after C++, it is almost guaranteed that you could do something along the lines of x.length or x.size or whatever that particular language has built in to be able to know what is the size of this collection list array, whatever it happens to be. But there is literally no way to do this in C++. Like, if I wanted to add 1 to everything in this array, I would have to pass in the size. This is the only way that I can do it. because there is, well, I shouldn't say there is no way, but this is the safest way, I should say, and the very common way. Like if you're looking at C++ code and you have an array being passed around, although usually it will take this form. Still 8. You will see it passed around, arrays passed around like this. You'll have the actual array that's getting passed in, and let me change the syntax on that. Preview for next week, I guess. You pass in the array, and you have to pass in the size of the array to be able to manipulate it. Now, potentially you can use what's called a null terminator. This terminology comes from C strings, which we'll talk about here later. But that's the idea of you have an array and you have a special value that indicates you are at the end of it. So for example, if I know for a fact that whatever array I am passing into this function, all of the values are positive, there are no negative values, I could use -1 as a null terminator. But we'll get into null terminators and C strings next week. All right, so now let's talk about the assignment. Okay, so two-part assignment on this. Part 1, the endless Fibonacci. Yes, I like the Fibonacci sequence because there's so many different ways that you can calculate it. It makes for a good punching bag for, well, showing the numerous different ways you can choose to implement something. And so the goal here is to write a function that will always return the next number in the Fibonacci sequence. And if you call the function multiple times in a row, it will continue to advance the sequence. The trick here is that A, the value of the sequence must be calculated in the function, and B, other than your initial variable values, you cannot alter the values in main. So for example, if I'm going to set x and y to the values 1, I am not allowed to change the values x and y ever again inside of main. But every time I call endless Fibonacci, I will get the next number in the sequence. So that exactly is what you need to do. You need to declare two variables, set their values to 1, call the function that you're going to create 5 times, and it should display 2, 3, 5, 8, 13. Doesn't have to be all in one line like that. You can have it in separate lines. That part doesn't matter. But, so yeah. Obviously, needs to use pass by reference here in order to make this work. Just think about it a little bit, and you should be able to get this one. It's not too difficult of a coding challenge. It's like 5 lines worth of code to get this one done. So, hence the 5 points on that. All right, the second one, and the one that will maybe take a little bit more effort, will be rebasing. So, as I mentioned in the lecture, sometimes you need to rebase data. So your data is in the range of 1 to 50, but you need it to be in the range of 15 to 35. Could be lots of different reasons as to why you need to do this. And so you need to write a function that will take an array and rebase all the values in that array. You need to display the values of the array before and after the rebase. And the array has to be defined in main and passed into the function. So all these calculations must be done in a function. So you're going to create an array of 10 integers. You're going to assign that array the values of 1 to 10, basically. So array of 0 is 1, array of 1 is 2, so on and so forth. Which, of course, means that your initial range is going to be 1 to 10 for your values. You are then going to prompt the user for a new minimum and maximum for the range. and then you are going to rebase the array to those values. So, for example, if the user enters a 20 and 80, your output would look something like this. 20, 80, here's the old values, 1 through 10. That should always be the same. And then here are the new values. Now, how you do this, it's a pretty simple formula. Again, assuming x is the value that you are converting, AB is the old range, CD is the new range. If you take x minus A times D minus C, take that quantity, divide by B minus A, and then take that quantity and add C to it, you will get the converted value. Again, where AB is the old min and max, CD is the new min and max, and then X is the number you are converting. So implement that. As always, if you have questions, make sure you post them to Blackboard. Otherwise, good luck with the assignment, and I'll catch you on the next video.